Hey everyone, today I want to talk about momentum, and specifically, how does linear momentum relate to angular momentum? First off, conservation of momentum is a huge idea. Okay, so let's just say conservation is huge. Okay, conservation of momentum is a huge idea, and that this is true, that momentum is conserved for any linear application, okay, in any type of collision, which we've already gone over. The same is true for angular momentum. Angular momentum is conserved for an isolated system or a closed system where the net external torque acting on the system is zero, same as the net external force was acting on the system during a collision. Then momentum was conserved in each linear direction. So angular momentum is going to be conserved here as well. And again, this is a huge idea as it relates to satellites orbiting a planet, planets orbiting the sun. Just to name a few applications and where you'll see this. But first, I just want to drill down on the differences between linear and angular momentum, and see how linear momentum relates to angular momentum for any particular point or axis of rotation that we're going to analyze about. And let's first start off with what we know already. Okay, so momentum from last year in a linear fashion is just mv. So the linear momentum vector is going to be equal to the mass times its velocity vector. And we also know that the angular momentum, L, capital L, was equal to the moment of inertia for a system times its angular speed. We're going to actually come back to and derive this here in a second. Where we're going to start with that is Newton's second law. So for the linear, we're going to have the net force is equal to the mass times the acceleration. And from a linear perspective, Newton's second law would be the net torque is equal to the moment of inertia times angular acceleration. Again, both torque and acceleration are a vector. Well, let's carry this through here for a second and see where we go. If we know that the net torque is equal to the moment of inertia times angular acceleration, there's another way of Newton's second law that we've now learned this year, in which case we've learned that the net force, and it's probably not as seared in as the other one is, but the derivative of momentum with respect to time is also the net force acting on a system. And likewise, the net torque acting on a system would be equal to the derivative of the angular momentum with respect to time. I mean, you can see the consistency here. Rotational moment of inertia, rotational inertia is the rotational equivalent of mass. Angular speed, should be a vector. Angular speed and linear speed, acceleration, angular acceleration. And here again, the derivative of linear momentum with respect to time is the net force. Derivative of the angular momentum with respect to time. Well, I said we were going to kind of come back to this and derive this here. Well, if we take this equation here, and I'm going to multiply both sides by dt. Okay, so I'm going to, well, first of all, net torque, I have both equal here. So let's just go ahead and substitute in. So the moment of inertia times the angular acceleration is also going to be, these are both net torque, set them equal to each other. The linear momentum with respect to time, the derivative of linear momentum, angular momentum, the derivative of angular momentum, looking at this L here, derivative of angular momentum with respect to time. So let's work backwards here and integrate this function. So let's bring this dt over. Moment of inertia is a constant, so I'm just going to pull that out, and then I'm going to integrate the angular acceleration with respect to time. Again, I'm just moving dt over and then taking the integral of both sides. So I kind of skipped a step here. Let me just show this, right? So I alpha dt is going to be equal to dl. Okay, all I did was move the dt over, and then I integrated both sides. And then since I, moment of inertia, is a constant, I can pull that out. Well, what is the derivative of the angular acceleration function with respect to time? Well, that is just the angular speed. And if I integrate dl, I'm just going to get L, which is what we have up here, such that the angular momentum is equal to the moment of inertia times the angular speed of a system. All right, so you know that. These are some different equations here. I just wanted to spend some time to correlate these two. Okay, that's good. We know that, but what does that have to do with linear momentum and angular momentum? So let's take a closer look at that. If I take, let's see, make sure we can see here. So if I take a lump of clay, all right, a lump of clay that is going to be moving along in this fashion here, and we're going to say that it will have its own momentum vector. All right, so it has its own momentum vector, which is going to be mv. Okay, so lump of clay with mass m has a velocity v, or a momentum vector p. And let's say that this is going to collide with a thin rod, okay, that is pivoting on its end here. It actually has no angular momentum initially. It's just staying there. There's a rod there that can pivot about this axis, the end of its rod. And so if this is my axis of rotation, potentially, what's going to happen is this lump of clay is going to collide with the end of this thin rod here. This thin rod, we're going to say, has a distance from the axis of rotation to its end as d. So you guys get me. What we're doing here is we have a lump of clay that is moving in this direction. It's dotted here in red. It has mass m, let's call it m1. All right, m1, and make sure that's clear there, m1, and it has velocity, linear velocity. So what is the angular momentum that this lump of clay has with respect to this axis of rotation right here? That's really the question. How do I correlate these two? As it turns out, there's an r vector, r. What is the r vector here? This r vector is the position of this mass at a particular time, as is shown right here. The distance, this is the r distance from the axis of rotation. Linear momentum has angular momentum with respect to this r and this angle theta, and that is defined. So the angular momentum for this object moving with a linear momentum is going to be equal to r mv, so it's linear momentum, times the sine of the angle between the r and the v vector, or the r and the momentum vector. So this r times this p. So you could also say, well, this would be true as well, right? So we would just say rp sine theta. So being able to figure this out, this is kind of just like the torque problems that we've worked on in the past. What does the sine function do? It gives us the perpendicular aspect of it. As this lump of clay is moving over, r is getting smaller and smaller and smaller. Well, guess what? The angle's also changing. So all that this angle, sine of this angle, is doing is giving me either this perpendicular component of the momentum vector, or it's giving me the perpendicular component of the r vector. Because isn't the sine of theta, like this is really, we could call this r perpendicular. This distance here is actually, you see the right triangle that this makes with respect to this? So the sine of this is equal to r perpendicular over r. So r sine theta is really just r perpendicular. It turns out, guys, that just like with torque and the r vector and the force vector, we could say that the angular momentum for this would be r cross p. And so if I have a three-dimensional r vector and I have a linear momentum vector that has 3 dimensions, how could I actually find the angular momentum about a particular axis or point of rotation? I can do r cross p. Well, what is p? P is the momentum vector. And so this also works out to be that I could say, if I pull the mass out, mass is just a constant, it turns out that r cross v, right? If I multiply m in there, I'm just going to get r cross p, which is what I have here. Again, this is for unit vector notation. If I have a three-dimensional r and a three-dimensional moment linear momentum vector, I can find the angular momentum using the cross product. But I'm not going to take the time to do this again. I showed that to you in the torque video. That's just utilizing the determinant matrix process to find a cross product between these two vectors. I just wanted you to see the correlation of this with respect to this. It's no different than torque being RF sine theta or R cross F for that matter. But let's get back to this problem. What if we need to find the final angular speed of the system after this collision? So lump of clay, mass m1 times velocity moving in this direction, so momentum moving in that direction. This r value again is changing. This does have angular momentum as it relates to this point, which, by the way, even if this wasn't here, this rod wasn't here, this lump of clay moving in this linear direction with a momentum vector as shown would have angular momentum with respect to this based on this distance d, whether or not this rod is here or not. Okay, it's going to continue on, and this is the perpendicular distance that takes care of this. So how do we go about doing this? Well, this is where conservation gets into it. All right, the conservation of angular momentum. Well, what is the momentum before the collision? Remember, this angular momentum is the same here. If I were to stretch it all the way out here, the r grows, but so does the angle. So as it's here, or whether it's right above here or right at the end, right before the collision, the angular momentum of this linear momentum is not changing. All that matters is this distance here, which is d, variable d, or the perpendicular r based on sine theta and r. So the conservation of angular momentum is the big picture idea. So the initial angular momentum is going to be equal to the final system angular momentum. Well, what was the initial angular momentum? Well, we have this rod is not moving, and we have the angular momentum of the lump of clay, which is just r mv sine theta. So r mv sine theta. Let's make this m1 to make sure we know which mass we're talking about. Let's also throw an m2 on this thin rod. Okay? Plus 0, because the thin rod doesn't have any angular momentum. It's not rotating. It's just sitting there waiting to be smashed by this lump of clay. Now the lump of clay is going to stick. So we have a completely inelastic collision, and it is going to stick right at the end of this thin rod with distance d. Well, what's the angular momentum of the system after? It's really the sum So we can say the sum of an angular momentum of a system would be the angular momentum of 1 plus angular momentum 2 plus angular momentum ... however many. So what I really have here is a point mass of lump of clay that's going to stick a distance distance d away, that's going to have its own moment of inertia. But any rigid object, this is going to now be one rigid object. Getting back to over here, the angular momentum of a rigid object, so this is for a rigid object with shape, has an angular momentum of its moment of inertia times its angular speed. So we had linear momentum for this guy we were converting to angular momentum based on this description that we just went over. And then we have this idea for the system after. So we have the total moment of inertia times the angular speed, because everything is going to rotate at the same speed after the fact, whatever that's going to be. That's what we're trying to determine here. All right. So at this point, let's use the different variables. So r sine theta is really d. This is the r perpendicular. Again, if I said sine of theta is equal to the perpendicular distance over the hypotenuse, opposite over hypotenuse, over r, if I move this r over, r perpendicular is just r sine theta. So that would be, let's say, dmv, m1v, is equal to, what's the total moment of inertia? Okay, well, I have this lump of clay with a mass, m1, the distance d away. Well, that point mass for that lump of clay is just mr squared. So m1 d squared plus, well, what's the moment of inertia for a thin rod from at its end? You know, you can go back to your sheet here and we can see that a thin rod with its axis of rotation at the end of it is going to be 1/3 ml squared, where L is the distance of the rod. And so this would be 1/3 m2. This L value here is d, so we're going to say d squared. And that is the total moment of inertia, and the whole system is going to be rotating with whatever this final angular speed is going to be. Well, we can already see that we can get rid of a d. So I'm going to cross out the d, get rid of the squares because I have one in each term. And then I'm just going to divide this over. So I have m1v on the bottom, and this whole thing is going to come over, and let's pull a d out. So I can pull a d out, and I have left would be m1 plus 1/3 m2. m1 plus 1/3 m2. And again, we're just deriving the angular speed for this particular collision, all in variable form, which is what we would find here. And using the conservation of linear momentum. Okay, so the big idea here is that angular momentum will always be conserved, just the same as linear momentum was conserved in any one direction when the net torque acting on the system is zero. And we need to fully appreciate and understand that objects that have linear momentum do have angular momentum with respect to a particular point in space, where something else may be rotating about. But again, whether this rod or not is here, or I chose to do here or here or here, this object with linear momentum does have angular momentum based on all of these equations here. So linear momentum does cause an object to have angular momentum about a particular axis of rotation. Guys, one other thing I wanted to mention here, I forgot to mention, was that when you're using these equations here, if you wanted to know the direction, this will calculate the magnitude of the angular momentum. But again, if I need to know the direction, I need to use the right-hand rule again. So I'm taking my right hand, and I'm going to follow the r value, the r vector direction, Then I'm going to curl my fingers in the direction of the momentum vector, which means my thumb is actually into the board or into the screen here. So right hand rule, curl, and goes down into the screen or into the board. Whereas if I'm using the cross product, it will actually tell me the direction of that linear momentum in I, J, and K unit vector notation, just like we did for torque. Okay, just wanted to point that out. Still using the right hand rule here to determine the direction of angular momentum.